So yeah, this talk was called the Functional Final Frontier. If you like, you can pretend that's what this talk is called. It's going to be somewhat related to that, but I think I want to give, in this sort of variation of this talk, some wider context. And actually, this talk could be called, immutability, interactivity, and closure script. But honestly, it could be called immutability, interactivity, and insert your language of choice. It doesn't really matter. The thing I'm interested in here is communicating the principles, not any specific language. So I, until recently, was employed at the New York Times for about 4 years doing front-end development there, and that was a lot of fun. My background is in doing user interfaces, all kinds of user interfaces. I've done user interfaces in Cocoa, and Java, and C++, but I spent the most time doing them in JavaScript. I now work at Cognitect, and I'm excited about that. Cognitect's a fun place because they're probably, of all things, they take immutability as like a sort of central tenet of all the things they design. Both, they're sort of stewards of closure of the language which embraces immutability, as well as a pretty interesting database solution called Datomic, which also emphasizes immutability. But I want to talk more specifically about immutability in the context of user interfaces. So object-oriented programming and user interfaces sort of came to be almost at the same time. I mean, objects did sort of appear in the late 60s, but it really wasn't until Smalltalk, until the variant that we're most familiar with came to be. And at the exact same time, the modern user interface also came to be. This is an image of some kids playing with a Smalltalk system at Xerox PARC. If you can fire up a Smalltalk image today, there's a very fantastic open source version of Smalltalk called Squeak. You can install it. You can write Smalltalk in it. If you open up the system browser, which allows you to see all the classes that are involved in the entire system, you would probably encounter the words model view controller, right? So that's pretty wild, though. So it's, that's, I don't know, that image was, the kids was probably from the mid-70s. So that's 30 years of MVC. And people have adopted this term when they're talking about web-based systems as well. But basically, the idea was first formulated by Trygve Reenskaug and Adele Goldberg at Xerox PARC in 1979. And it's had an extremely long shadow. The basic concepts are still prevalent today. If you're doing front-end development, it doesn't really matter if you're targeting iOS, Android, JavaScript. MVC is a very popular way to organize user interfaces. And that's because I think at a very abstract level, MVC is an extremely sound separation of concerns, but implementations leave much to be desired. We haven't really advanced much further beyond what they came up with at Xerox PARC, which is pretty sad, given that's 30 years old. And the thing I'm going to question here is I believe that we can get all the benefits of traditional MVC systems, but we can eliminate this thing that I do not like about the implementation, which is that MVCs are constructed on top of stateful objects. And you're probably thinking, how could you do that? How can you get all the benefits of MVC and eliminate something that almost all modern MVCs have, which is that they're constructed on top of stateful objects? So to throw a wrench in this history of UI programming, though, which plays into this talk because we're going to be sort of emphasizing web browsers, is Tim Berners-Lee invented this thing called the web browser in the late 80s on a Next machine. So Next at the time had one of the most powerful MVC frameworks, Next Step. It eventually became Cocoa, which is also now everybody knows about because of iOS. But he took this rich MVC desktop system, and he built the world's first browser, web browser. And the idea behind web browsers was not, I want to build rich user interfaces. I want to hyperlink documents over a network. That was the only thing it was meant to do. Hyperlinked textual documents which are rendered, right? There was no point in solving the rich user interface issue here. That wasn't a goal. It was a completely non-goal. So I don't think he foresaw a future where most people interact, or not most, but many people interact with the web through the document object model. If you've done any serious work on the web, this is more or less why your life is terrible. Because the document object model is fundamentally about documents. It is not about user interfaces. It's not about events. I mean, these things are just not meant to, they're designed, the DOM was designed to solve a different problem. And so when I look at the sort of landscape of what people are doing with web browsers and the DOM and JavaScript, you know, it really feels a lot like this, right? Alan Kay has this really great analogy where he says software architecture too often looks a bit like the Great Pyramids, right? It's very impressive to look at, but there's no deep conceptual idea here, except, you know, it's going to take thousands of people, hundreds of years to build, right? So often software feels like this, and he makes this interesting claim that often what's missing from software development is one tiny, simple idea, and then you can have a radically different architecture. You can have a much more efficient placement of architectural material. And he points out that it was the arch, right? This extremely simple concept permitted humans to build a completely different type of building. And so I think, you know, if we're going to do UIs, we're looking for this arch. I don't think we found it yet. MVC is a good starting place, but I think there is something missing. So object-oriented programmers got their chance. They came up with MVC. That's awesome. But we need something more, and so maybe we should look at what the functional programmers are doing. So there's a thing called functional reactive programming, FRP. It's still a very active area of research. If you're into Haskell, you would have heard of this. It's fairly academic, and they have lots of problems they still need to solve to make that work. There is a stateful object-oriented take on this, which is getting really popular now, called RX from Microsoft. RX Java, RX Cocoa, all this stuff, it's the object-oriented take on FRP. It's very interesting, definitely awesome for coordinating events and complex asynchronous workflows. However, it doesn't really solve the problem that UIs encounter, which is that how do we deal with the fact at the edges of our sort of system, we have to render something. The user has to see something. If you're coming from Go, the Go programming language, or if you're into Clojure, Clojure has this thing called core async, then you've probably heard of CSP. This is Tony Hoare's abstraction. But again, it's also a coordination language. It doesn't really address the rendering problem. So you might be thinking, well, maybe MVC is it. Maybe there's nothing more. Maybe we're just stuck with stateful objects, and we have to sort of erect these pyramids of user interfaces that are hard to modify, hard to extend, hard to maintain. Maybe there is no arch. And I would argue, from having played around with Clojure for a long time, and this is probably old hat for people who have played around with Haskell or Scala, but there's been an amazing amount of incredible practical academic research gone into something called persistent data structures, which I'm not going to assume that you guys have heard of. And I want to talk about them now because I think they give us an opportunity to simplify the coordination of state in user interfaces, which I think is the main source of complexity in a complicated user interface, is that you have lots of stateful components. How do you coordinate them? How do you know who's changing the state? And I think persistent data structures can sort of make this tractable. So I'm going to show some slides. These are not my own slides about how persistent data structures work, just to give you sort of a sense about how I'm able to accomplish what I'm about to show you. These slides were done by Zach Allen of Hacker School, which is a really awesome sort of like coders, like a code writers retreat in New York. So stealing his slides. So functional programming and data. Functional programmers like data. They like immutable values, not mutable objects. Whenever you change something, change, right? All you mean is you're going to modify something and get a new value. You're not going to change the original things. So it's not like you get an array and you mutate the thing at the second index. The old value that the array represented is now gone forever. We don't like that. So this is where the word persistent comes from. And the cool thing that I'm going to demonstrate is that starting in the early 2000s, because of a paper by Phil Bagwell, we now understand how you can do this efficiently. So I'm assuming everybody's seen a linked list, and you might be saying, that's so boring. That's like, data structures 101. But linked lists have a really cool property if you treat them in an immutable way that demonstrates how persistent data structures work, the ones we use in Clojure and the ones that are used in Scala and Haskell. So a linked list, you've got something at the head, and it points to other items in that linked list. Well, the neat thing about a linked list is if I have a new head and I point to X, what's cool about this is that I have two distinct values, right? But these two distinct values actually share three elements, right? They're actually sharing memory here. So even though Y represents the list with the Y on the head represents a particular value, it didn't destroy the value that X represents. Now you could imagine that I could get the tail of X and then cons Z onto the head of that, and now I have three distinct values, but they all share more than 50% of memory. Right? This is a really cool property of linked lists. Structural sharing. So sharing structure gives us space efficiency, but it also gives us computational efficiency. When we update something, it means that we can update something without having to update, without having to do copy on write. So this is a traditional technique, is that if I have some data structure and I want to update it and I want to appear to have immutability, we simply copy the whole thing. Of course, when you get to like a million elements, right, that's not efficient. So persistent data structures allow us to update a large data structure in a functional way, and we're going to minimize copying. And that might not be obvious how to do that, and I'm going to show you. So Phil Bagwell, who sadly passed away, came up with this thing called the hash array map trie. He wrote this paper in like 2002 at EPFL, where Scala was created. And he had come up with a mutable variant. Rich Hickey read the paper, was like, this is fantastic. Just by tweaking it a tiny bit, we can create an immutable variant of this data structure. So I'm going to show a simpler version, a simpler variant, not the hash array map trie because it's a bit complicated. But I'm going to show you how we can have an immutable array-like type. So it has all the properties we like about arrays. It's random access. Like an array list, you can append to the end efficiently. You can split them efficiently, and so on. So the idea here is that data lives in the leaves, and the way that what a bitmap vector tree really is just a tree of arrays, right? It's just a tree of arrays, and it's going to be a prefix tree that we use to find any particular element. But it's going to be a bitwise prefix tree. And let's see what that looks like. So let's pick some arbitrary size for our nodes, arrays with 4 elements in them. So each element of that array points to another array of the same dimension. Each array of that points to another 4 arrays of that dimension. And then finally, we hit the leaf nodes, where our values live. And here we just have the numbers representing the indexes, right? So how do we find something in this? And we said it was a prefix tree. So get index on that. So imagine I want to find the 106th element in this representation. Well, that number has a binary representation, and we can mask off the bits to get to where we need to be. We mask off the first 2 bits. This is the index 1. So we descend down here. We mask off the next 2 bits. That's index 2. It's 2 again, and it's finally 2, right? So in order to get there, what did I have to do? I had to do 3 array lookups and some bit masks. This is stuff that the JVM and modern JavaScript engines, this compiles down into x86 instructions. This is going to be very fast. So what about updating? So if I want to update, what do I have to update? I only have to update the root and any nodes on the path to the thing I need to change. And here I'm going to replace 106 with the string foo. All those other nodes, right, they're not going to change. And then you're probably thinking, well, that's, what, 4 to the 4th? What is that? So that, if we have the vector, the node size 4, we can hold 256 elements. So that seems OK. So as it turns out, if you do a bunch of empirical testing, 32 is a great size. It's a size in which lookup and updates are sort of in an optimal ratio. This is an image from a Bagwell paper that took Rich's variant and they further extended it. Just to give you a sense of how good 32 actually is, imagine a persistent vector which has 32 levels of nodes, or sorry, 7 levels of nodes where each element is 32 wide. That's 32 to the 7th power. That's 34 billion elements on a 60, even if this was a flat array, on a 64-bit virtual machine, if every element was an object pointer, that's 256 gigs of RAM, right? So to update a data structure this huge, we only have to, at most, do 7-bit operations and 7 array accesses. To update anything in this massive data structure, we only have to replace 7 arrays. So hopefully this has convinced you that structural sharing is really awesome. OK, so now you get the idea. So this is how we're going to be able to play this game. So now that we have the data structures that are suited to represent immutable values, we can do some really cool stuff with user interfaces. And so I wrote a library called Ohm. And what I did was I said, we can couple, in this case, ClojureScript, which has a suitable persistent data structure library. And we can couple it with React. And React is a relatively new, on the scene, library for rendering. It doesn't really do MVC. It's very much focused on rendering. But the way that their algorithm works is extremely suited to pairing with persistent data structures. So the way that React works, React is sort of like, when you use it, you're like, this looks object-oriented, but actually it's object-oriented if a functional programmer had to write a library in an object-oriented style. So what it effectively lets you do, it lets you take your data, which you can assume is your app state. You can apply a function, and then React will generate more data. And this is what's called the virtual DOM. So React doesn't actually change anything. It creates a new data structure. So if I have some data at time 0, and I apply a function, I get the data structure that represents my interface at time 0. Now, if I update the data, we don't destroy the old data. Right? We're not destroying the old data. We're simply new data that represents the new state of the application at time 1. I can apply the same function, and now I get the UI at time 1. So what React does for us is it calculates the diff. It takes the 2 virtual representations of what the UI should look like, and it calculates the minimal set of changes to actually make to the DOM. And it does this efficiently. It's like it's lazy, and the subtree calculations only looks at what it needs to look at, and so on. But what's cool about this is what happens if I flip v0 and v1. React will, for free, give me the reverse set of changes. Right? It's just free, because that's just the way diffing works. Right? So I can go back in time, and I don't have to write any code for this. React just gives us time travel by definition, by the way that it works. You might be skeptical. I'm going to show a demo, and the demo is pretty cool. So really what it does is your component tree looks something like this. And React, and the way that React makes diffing tractable is that they simplify the what gets diffed. So you can imagine the blue guy is a div. And here we see, oh, it's a div at time 0, and it's a div at time 1. And we're like, well, nothing's changed there. Then we descend into the children. And we see, oh, now we have 2 paragraph tags. Well, they don't look different. And then we descend into the children, and we see, oh, there was a span and then a font tag, but they switched places. And so what does their algorithm do? It simply knows to move those 2 DOM nodes, right? And so again, this should show you that we can go in either direction, right? And it's driven by data. So let's see a demo of this. So once I realized that persistent data structures and React were a good pairing, I was like, I wonder how hard it would be to do undo. So I've been doing MVC-style programs for a very long time, and I really hate doing undo. If you've ever looked at Coco's undo manager, number one, it's hard to get right, even if you plan for it up front. retrofitting undo onto an existing object-oriented system, good luck. That's, whatever. It's not going to happen. But if you start off with a functional model, I added undo. So I took the very sort of traditional benchmark MVC application, which is to do MVC. It's not very interesting, but I said, how hard would it be for me to add undo to an existing system? And so basically there's like this is like 5 lines of code. I wrote 5 lines of code. I had an existing version of to do MVC in Ohm already. So I wrote 5 lines of code, and then I got this. So here I can go go to, milk, walk dog, So I can click here. I can switch tabs. I can clear completed, go like this. I don't know why you would walk a cat, but just for fun. So up here you see that it's not slow. This is far faster than 60 frames a second. So 60 frames a second is like 16 milliseconds. So I can click undo. That's it. And I didn't have to plan ahead for that. Right? There was no planning ahead for this. This falls completely out of saying, I'm going to represent my app state with persistent data structures. I'm going to let React calculate the changes to the DOM. So you might think, well, undo, who cares about that? It is actually pretty cool, but maybe your app doesn't need undo. But think about error handling. What happens when you can't communicate to the server and you need to roll back? So what do? I look at somebody's program and see, oh, they had to manually roll back their app state. Or say a customer has an error, right? What can you do in this model? You can actually serialize the last 50 steps, send it to your server, and play it back. It's trivial, right? You don't have to write code to do this. All these things that we want to do around error handling and rolling back, these also fall out of the ability to travel freely through time. So I could talk more about things that I've done, but I think it's more fun to demo something that somebody else did. So this was from one of the developers of Ableton Live. He sort of ran across my blog post, and he was like, OK, that sounds cool. Here's a little toy MVC app, and it has undo. And he said, I'm going to do something less toy-like, because I don't really believe David Nolen. He seems smart, but this seems like too much magic. So he said, I want to build a 64 by 64 pixel editor, and I want to see how much effort it's going to take for me to add undo, redo, and then like a time-traveling preview, right, to my app. And will it still be simple? So here we've got his pixel editor. So this is his. I did not write this. This is somebody else. So I can pick some colors here. I can draw a little circle. Over here on the right, you see all the events piling up. Let's go like this. OK. So if you notice on the left, I can scrub, and it's going right back over the timeline. We can move forwards through time. So this image is actually a persistent vector that has 4,096 distinct values, right? So he's encoded 4,096 individual pieces of application state, right? So between each step, you would assume we'd have to replicate all 496 values. But I explained to you how persistent vectors work. It's not true. So even if I click like this and I'm dropping like this, right? The difference between this one and this one, it's like, again, maybe it's 4 or 5 arrays, right? There's not much difference. Persistent data structures naturally represent the delta. Pretty cool stuff. So he's also able to here. He has this really cool thing where, because it's encoded inside of these persistent data structures, doing things like producing an animated GIF from what I just drew, again, trivial to do. Well, and you're probably wondering, well, how much code did that take? So this is this is actually all the code. It's like less than 50 lines. This is the whole thing. You can almost, if you're in the front row, you can actually read it. And I think that's pretty amazing. This includes undo, redo, and the time travel preview. So I think that's a pretty awesome radical decrease in complexity. If you've ever done undo before, much less in a pixel editor, you know it's not very fun. What's also cool about this is that you're probably thinking, well, how much memory does this really take? Maybe you're like, okay, this sounds like it's going to be good, but really, how much memory does it take? So I made a little memory test using the Chrome developer tools heap profiler. And so I snapshot the application right when it starts, and it starts at about 3.8 megabytes of memory being consumed. On the right, what I did was I said, well, I'm going to take a JavaScript array. I'm going to stick, 4096 sized array. I'm going to stick strings in it, and I'm going to change one value. Of course, with a JavaScript array, all I can do is copy it every time. So copying it 100 times with a different value everywhere, that consumes about 1.7 megabytes of memory to hold 100 distinct pixel images. On the left, we see that doing the same thing with a persistent vector, 0.2 megabytes, right? So I don't know, what's that, times 8, 9? It's 9 times, it's almost an order of magnitude smaller, the amount of memory being consumed. That's pretty cool. So efficient in time and space. If you haven't seen Ohm before, I definitely recommend checking out. It's available on GitHub. I don't know how many people here are familiar with ClojureScript or Clojure. Though these ideas are extremely portable to other languages. For example, I know that the Scala guys are using Scala.js, and Scala has very good persistent data structures. I've seen some awesome demos where Scala.js plus React works great. Even if you're a JavaScript programmer, you can do what I'm demonstrating. So there's a fantastic, not fantastic, my library, but it's just exporting ClojureScript to be consumed by JavaScript consumers. So maybe you're in JavaScript and you can't, or maybe you're in CoffeeScript, right? I don't know what you're using, but you want the data structures, but you don't want to have to adopt the language. So Mori exports in a very underscore-like way all of the persistent data structures as well as the entire standard library for manipulating them. Quite a few people I know are actually using Mori in their client-side apps because they want to be able to pair React with immutable data structures because, again, React gets a lot better if you pair with immutable data structures. So that's actually all I had today. I think I'll take some questions.
Does this work with MVC frameworks, or is this instead of using an MVC framework? So
that's what I was trying to suggest. So you can I know people are, sorry, the question was, does this replace MVC frameworks, or can you use it with MVC frameworks? So they are in some sense orthogonal. So what I'm saying is you can have the MVC architecture. You can still have models which represent the domain. You can have controllers which coordinate between a view and the domain. That's fine. But instead of having mutable models and mutable controllers and mutable views, this is how you can replace every part of that stack with immutable things. So people have played around with Ember. I've seen some experience with Ember. You got Ember plus an immutable model. You can do this. Again, it's going to require some unlearning, though, right? There are a lot of things that people do in these traditional systems that are kind of are swimming the wrong direction.
But who owns the model? The MVC system has its own model that it controls. Sorry, I'll just repeat. So who owns the model? The MVC framework obviously has its own copy of the model, and this is keeping a version history of those models. How are the two systems interacting with each other?
So those are orthogonal, right? So what I tried to demonstrate with what I was doing is that I was able to build a 2D MVC application. The undo is a separate thing. That's completely separate. If you don't want undo, you don't have to do that. I think there's somebody behind you.
You mentioned at the beginning that you had done Cocoa, iOS, and and Mac. Have you tried or have you thought about if it's possible to sort of apply this to sort of native mobile or other frameworks?
So it's definitely worth experimenting with because, so the question was, has this been applied to like Android or iOS? So it's definitely worth experimenting with. In iOS, it's a bit easier to actually just use React, but that's because OS 10 and iOS 7, OS 10 Mavericks and iOS 7 now export JavaScript core so that you can directly bind from JavaScript to native Objective-C. So I think there's a lot of cool things you could do there by literally just loading React and having React manipulate Objective-C objects.
Is there any sort of case that really aggravates the behavior of the React or OM structure? Are there things where you would definitely stay away from it?
I mean, so it does. I mean, it is pretty intensive. I will say that like it benefits from FastGC, definitely, same as Clojure. It benefits from jitting JavaScript engines. Granted, I mean, a ton of work has gone to React to make it work even if those things aren't present, and same with ClojureScript. We test on slower JavaScript engines, but it's going to be slower than like mutating an array. If there's something you're doing where you just need to like mutate something, do it. In fact, the pixel-based editor, what does it do when it blitz, right? It's just mutating the canvas. We don't need to get in the way of that. So part of what I'm suggesting is that this works best when this is your domain, this is your model. You don't need this for like high performance algorithms. Does that answer your question?
Yeah. Any other questions?
Then thank you very much, David.
Thanks.